Today, we are diving into a really fascinating and frankly pretty bold theory. What if all the mind-bending complexity of our universe, every single particle, every force, could emerge from just one simple geometric object with absolutely no numbers that need to be tweaked to make it work? Now, to really get why that's such a big deal, we have to start with one of the biggest questions in physics. Why? Why are the fundamental laws of our universe built on numbers that we have to go out and measure, but that we can't actually explain the origin of? You see, our best theory of reality, the standard model of particle physics, is an absolute triumph. But it has a kind of dirty little secret. To make the equations actually line up with reality, physicists have to manually plug in almost 20 different numbers. These are things like the mass of an electron or the strength of a force. We call them free parameters. The theory doesn't predict them, it needs them to function. So to see how this new theory tries to solve that huge problem, here's our game plan. First, we're going to dig into those so-called magic numbers in physics. Then, we'll introduce this radical idea of a universe built from a single shape. From there, we'll see how it claims to explain why matter comes in threes, how it reveals a near-perfect formula for particle masses, and how it even gives us the recipe for how particles interact. And then, we'll wrap it all up with a final scorecard. Okay, first up, physics 19 magic numbers. Let's really get to grips with the problem that's sitting right at the heart of our current best theory of reality. So, the standard model depends on these inputs. Things like the mass of a particle, the strength of a force, or these mixing angles that tell us how particles can transform into each other. And look, we've measured these values with incredible precision. But, and this is the absolute kicker, the theory itself gives us zero reason for why they have these specific values. They aren't answers the theory gives us, they're questions we have to feed into it. They're inputs, not outputs. So what if there's a totally different way to look at this? A theory that doesn't need any of these numbers to get started? Well, this brings us to a really interesting new idea called unified dynamics. This new approach, unified dynamics, proposes something, well, pretty radical. It claims that everything, and I mean everything, space, time, matter, the forces, it all emerges from the properties of this one incredibly simple shape, the tetrahedron. It's the simplest 3D solid you can make. This is it, the single proposed building block of all reality. So the whole mission statement is right here, and it is incredibly ambitious. 0 free parameters, 1 tetrahedron. The goal is to get from this one shape to all the known laws of physics, with no magic numbers, no knobs to tune, no cheating. All right, let's put this idea to the test. First big mystery. Why does matter come in 3 distinct families or generations? We have the electron, its heavier cousin, the muon, and its even heavier cousin, the tau. Why 3? Why not 2, or 5, or 17? Now, this is where it gets really, really cool. The theory doesn't just guess the number 3. It derives it from pure geometry. It all starts with the rotational symmetries of the tetrahedron, the ways you can turn it and it still looks the same. Mathematically, this forms a group called A4. Then, you find a special subgroup inside of that, called V4. Now, here comes the magic trick. When you perform a mathematical operation called a quotient, basically dividing the first group by the second, a new structure pops out. It's called Z3. And that Z3 structure has, you guessed it, exactly 3 elements. Unified dynamics proposes that these 3 mathematical elements are the 3 generations of matter. And this just perfectly illustrates the power of the idea. The number 3 isn't some arbitrary input anymore. It's not a free parameter. It's a direct, necessary consequence of the tetrahedron's geometry. It has to be 3. Okay, so the geometry forces matter too. Matter to come in 3s, fine. But what about their masses? The electron, muon, and tau have wildly different masses. And the standard model just kind of shrugs its shoulders and says, that's just how it is. Unified dynamics claims the tetrahedron knows why. So the theory derives this fundamental rule, and it's baked right into the geometry. It leads to something called the Coid ratio. You can think of it like a strict geometric law. It says that the masses of related particles, like our 3 leptons, they can't just be random. They have to fit together in a very specific mathematical way. And for a 3D object, like the tetrahedron, that ratio is mathematically locked in at exactly 2/3. So how well does this geometric rule actually work in the real world? This is where things get a little spooky. If you take the known mass of the electron, the lightest one, and you plug it into this rule, The theory spits out predictions for the masses of the other two, and the result is just stunningly accurate. The error is less than 1/100th of a percent. I mean, just look at these numbers. The predicted mass for the muon is off by a mere 0.0065%. For the tau, it's even more precise, an error of just 0.0016%. This isn't just a good guess. This is a level of precision that makes you sit up and pay attention, especially since it's coming from a theory that started with 0 tunable knobs. But the explanatory power doesn't stop with masses. The theory also claims it can derive the relationships between different particles, specifically the rules for how quarks can transform into one another. And this is where the theory gets really elegant. That exact same Z3 geometric structure, the one that demanded 3 generations and predicted their masses, also appears to govern how quarks mix together. In the standard model, this is described by a complicated tool called the CKM matrix. This theory says that the CKM matrix is just a direct reflection of that Z3 geometry. And from that one single idea, it can calculate a key mixing parameter, the Cabibbo angle, and get it right to within 2% of the measured value. Okay, we've seen some pretty jaw-dropping results in isolation. So let's zoom out and look at the whole scorecard. How well do the predictions from this zero-input theory actually hold up against the measured reality of our universe? And wow, what's really amazing here is the sheer breadth of these predictions. We've got the strength of the strong nuclear force, predicted with just over a 1% error. Then there's the Weinberg angle, a key parameter in the electroweak force, predicted to within 0.19%. It even predicts the vacuum expectation value, which kind of sets the energy scale for the whole universe, with only 0.2% error. And of course, down at the bottom, the Koide ratio and the number of generations are derived exactly. So here's the bottom line. The standard model describes our universe with incredible accuracy, but it does so using numbers that it can't explain. This theory suggests those numbers aren't arbitrary at all. It suggests they are the inevitable, necessary consequence of the single, simple shape. And that leaves us with a pretty profound final question. Is our universe at its most fundamental level built not from particles or fields, but from pure geometry?